Welcome to the second session on machine learning and side channel attacks. The first talk is entitled Perceived Information Revisited 2, Information Theoretical Analysis of Deep Learning-Based Side Channel Attacks by Akihito Rei Ueno and Naofumi Oma, and the speaker Akihito.
Thank you for kind introductions. I'm Akihito from NTT Social Reference Laboratory in Japan, and I'd like to talk about our papers and try to perceive the information revisited to information theoretical analysis over deep learning side channel attacks. This is a joint work with Rei Ueno from Kyoto University and Naofumi Oma from Tohoku University. Okay, so I'd like to first explain the difficulty of evaluating the DLSCAs. So you know DLSCA is one of the most powerful side channel attacks, and many studies have recently focused on the DLSCA. And in general, training the neural network model requires performance metric. For example, there are various architectures, MLP, CNN, LSTM, recent transformers. And to determine which architecture we should use, we need a performance evaluation metric to evaluate these architectures. Also, when training the neural network, we need we usually use early stopping. For example, this figure shows running curve of the neural network. And we would like to usually avoid underfitting and overfitting. So we usually use a neural network to train the neural network at adequate number of epochs. And to determine the adequate number of epochs, we need to evaluate the neural network, train the neural network adequately. However, it is known that the major metrics such as in the machine learning, such as cross entropy and accuracy and score and so on, are not suitable for the side channel attack. For example, it is known that the model with the accuracy of 0% does not mean the DLSCA will fail. So therefore, we need to use a conventional performance metric for side channel attack, such as the success rate and guessing entropy are used for evaluating the neural network. However, you know these metrics are computationally expensive because to evaluate these metrics, we need to repeatedly calculate the scores of the output. So therefore, some conventional studies propose alternative metrics using the information theoretic theory based on the information theory. And one of the most well-known information theoretic metrics is mutual informations. So mutual information can give the upper bound on the attack performance. Now, intuitively, mutual information represents how much information about X can be obtained from the Y. For example, let X be we represent whether the person carries an umbrella, yes or no, and let Y be whether this afternoon is sunny or rainy. In this case, IXY quantifies how much knowing whether the person carries an umbrella reduces uncertainty about weather this afternoon. Or if someone has umbrellas, we gain some information about that rain is more likely. In this way, in side channel attack, we let X be a side channel information and Y be a secret key. And in this case, IYX represents how much information about the secret key is contained in the side channel information. For example, if IYX is equivalent to the 1 bit, then the roughly 8 observations will be needed to recover the secret key of the 8 bits. So in this way, the MY can give the limit of the attack performance And in this sense, MRI is an ideal metric, but estimating MRI is known to be difficult in practice. So there's alternative metrics have been proposed. So the first metric is perceived information, PI, which was proposed in Eurocrypt 2011. And it is defined as a difference between the entropy with the intermediate value Z and the loss value like this. So PI, theta is model parameters, and HZ is entropy with the intermediate value, and the last term denotes the log likelihood of the model Q seat, where the Q seat is a probability distribution of the models. And actually, this entropy of the intermediate value can be easily estimated because usually we assume that the Z follows the uniform distribution. So therefore, this entropy value is determined by the roughly the bit length of this Z. And this final term, the last term, can be is roughly equivalent to the test loss value of the models. Therefore, this perceived information can be easily and quickly estimated by calculating the test loss value of the models, but it is known that perceived information is highly inaccurate to estimate the mutual information. So to overcome these problems, we proposed in effective perceived information API in CHES 2022. And it defined by modifying the PI with a temperature parameter bait like this. And the EPI can be estimated quickly, and it can accurately estimate the performance of the neural network. However, there is no theoretical validity with this metric. So, therefore, in this talk, we propose a novel metric latent perceived information, LPI, instead of these conventional metrics. And the LPI is a theoretically valid metric for DLSCAs, and it is defined as a mutual information between the model's latent representations and intermediate values. And a success rate and guessing entropy can be bounded by LPI. Specifically, success rate can be bounded by from LPI, and guessing entropy can be bounded from below by the LPI. So LPI can be used as a performance metric. And we also propose a fast estimation method of LPI using the logistic regression. Okay, before explaining our metric, I'd like to first explain the relationship between the mutual information and the success rate of the side channel attack. And the side channel attack can be, it is known that the side channel attack can be modeled as a communication channel like this. In these channels, we assume that attack on the first round of the AES. So the target intermediate value of the in this channel is intermediate value output of the S box, and the K is a secret key, and the T is a plain text, and in these channels, K and T are XORed, and the output of the XOR is inputted to the S box, and the information over intermediate value is leaked out through the side channel X, and usually the attacker acquires the side channel traces and the corresponding plain text, and he estimates the secret key using these information. The important point of this communication channel is the maximum transmittable information of the secret key is bounded from the avoid by IZX. And from this fact, the CHES and his colleagues proved the following inequality. So this inequality gives a relation between the success rate and the mutual information and the number of the trace. So The right-hand side means information available with M traces, so, which is denoted by the M times IZX. And the left-hand side shows how much entropy attacker needs to achieve the certain success rate. And to explain this left-hand side, please look at this figures. This figure shows a plot of the CSR when the key length is 2 bits. So actually, this function XC converts the success rate to the amount of the information for achieving this success rate. For example, if the success rate is equivalent to the 0.25, then the CSR is equivalent to the zeros because we need no key information to achieve success rate of the 0.25. So in this case, we assume that the key length is 2 bits. Therefore, the random guess is sufficient to achieve this success rate. Therefore, the CSR is 0. On the other hand, if success rate is equal to 1, then we need all the key information to achieve the success rate of 1. Therefore, the CSR is equal to the 2 bit. So in this way, the left-hand side gives the amount of the information to achieve the key information to achieve this success rate, and therefore this equality gives the relationship between success rate and mutual information. Okay. So, however, there are some limitations of this equality for model evaluations. The first, the program is that it is hard to evaluate the attack performance of the given models. So you can see that from these figures. This figure does not contain the specific models. In other words, this communication channel is generous. So therefore, this derived inequality also provides only an upper bound of the strongest attack, not for the specific models. So therefore, we cannot use this inequality for evaluating the specific models. And the second problem is IZX is hard to evaluate due to the cost of the dimensionalities. So the side channel trace X usually contains 1,000 to the 10 of the 1,000 samples. And the difficulty of estimating mutual informations usually grows exponential with the dimensionality. So therefore, this equation, this inequality, it is difficult that this inequality is used for the evaluation of the neural network. So to address this, we introduced a new communication channel which includes a neural network. So this is introduce the new channels, and you can see that this channel includes a neural network, and we assume that in these channels, neural network can be divided into 2 parts, feature extractor and classifiers. And in this case, we also have the following inequalities. So, and this inequality looks like very similar to the previous one, but in this equality, left-hand side includes the variable f, which is related to the neural network. So this inequality can be used to evaluate the performance for the neural network. And we refer to as the mutual information between ZF as the latent to perceived information. And estimating LPR is easier than IZX since the dimensionality of F is usually much lower than that of the X. So in our paper, we introduced 2 estimation methods of the LPI. The first one is based on the KSG estimator, which estimates mutual information. So in this method, we use a k-nearest neighbor. to directly estimate the joint probability distribution (PZF), and and the KSG estimator can accurately estimate the LPI with sufficient traces. However, the computational cost of a case estimator is very high. The second method is a logistic regression-based estimation, and it estimates the conditional probability distribution PZ given F using a logistic regression, and it is very fast, but it gives only the lower bound of the LPI. So to confirm the validity of effectiveness of our method metric, we conducted some experiments, and I'd like to explain our experimental setup. So in our experiments, we use two implementations. The first one is a software implementations. It is a first order Boolean masked AES implementation provided in the ASCII, and it mounted on the Atomerix Mega 128D4AU 8-bit microcontroller. And we acquired 100,000 traces for training and for attack phase, respectively. And the second implementation is a hardware one, and it is first order Boolean masked AES with threshold implementation, and we use the 1.5 million traces for training and 500,000 for the attacks. And we use when evaluating the LPI, EPI, PI, we use a test set in this experiment, and we also estimate the lower bound on the required number of traces using this inequality. This can be obtained by dividing both sides of this equality by IZF. Okay, so I'd like first to explain the evaluation results for the software implementation. So this left figure shows LPI, EPI, PI estimation results of the neural trained neural work at each epoch, and this right figure shows attack number of the traces required for a success rate of 0.9 using the trained neural network at each epoch. And the other, so this yellow curve shows actual attack results, and the other curves shows lower bound estimated by these metrics. And the first, I'd like to focus on the PI values. So you can see that PI decreases after around 50 epoch. However, the attack performance shown in this yellow plot does not change. So therefore, this indicates that PI fails to reflect the attack performance. And I'd like to highlight estimated LPI values by KSG and logistic regression. So in the figures, this purple curve denotes the LPI estimated by logistic regression, and this gray line shows the LPI value estimated by KSG estimator. And you can see that the gap between these values roughly small. So therefore, logistic regression can estimate the LPI values accurately. So therefore, logistic regression can replace the KSG estimator for estimating case LPI. And finally, I'd like to focus on the this lower band derived by the EPI and LPI. So you can see that this so lower bound estimated by API and LPI are proportional to this yellow curves. So therefore, these metrics can successfully estimate the actual attack result. Okay, then I'd like to explain the result for the hardware implementation. So in this, so I'd like to first focus on the PI values in the figures, and you can see that PI remains close to the 0 across epochs. However, you can see from these figures at almost every epoch, or almost all epoch, neural network can retrieve the secret key. Therefore, the PI also fails to estimate the attack performance. And on the other hand, please look at, I'd like to highlight the gap between the actual attack results and lower bound estimated by LPI values. So, so you can see that there is a big gap between these values. So that this yellow plot and purple and there's a purple and gray. So this means the performance estimated by LPI is very imprecise. So, and I'd like to explain why LPI provide a loose estimate of the attack performance in the next slide. So to explain these reasons, I'd like to show our communication channels again. So as I mentioned, LPI is defined by the mutual information between intermediate value and this output of the future extractor. And you can see that this classifier is not included between these variables. So therefore, LPI does not account for the model's classifiers. So therefore, attack performance may be low, but LPI can still be high if classifier is poor. In other words, replacing the classifiers with a more proper one, we may be able to improve the attack performance for the models. So there is a room for the performance improvements. So to confirm this, we conduct experiments with replaced classifiers. So we use logistic regression trained on the training set as final classifiers. So these left two figures shows experiment results on the software implementation for the at epoch over 50 and 100, and the right two figure shows experiment attack results on the hardware implementation at epoch over the 250 and 500. And you can see that's the gap between, and in the figures, this purple plot shows the attack result with logistic regression, and this gray line shows attack result, original attack result. And you can see that the gap between these values is very small in the software implementation, but in the hardware implementation, there is a gap. There is a big gap between these values. So this means classifiers for neural network on the hardware implementation was not trained sufficiently. Okay, so let me conclude my talk. We propose a new metric called latent passive information for the evaluating trained neural network. And it provides a upper bound on the success rate and a lower bound on the number of the traces for required to achieve the certain success rate. And it is a theoretically validated metric. And we propose a first estimation method for the LPI using logistic regression. And however, in this talk, we usually use a neural user conducted experiments on the attacking on the AES. However, there are various ciphers and implementation. So we need to investigate the various implementation in the future. That's all. Thank you.
Thank you for the talk. We might have time for just one question, if there is any. Let me ask one question. So you propose two methods to estimate the LPI, the one with the logistic regression and the one with the MI estimator. I was wondering how much faster it is to use the logistic regression compared to the MI estimator.
Thank you, your question. I'm sorry, I forget the detailed processing time of these methods, but so if I remember correctly, so logistic regression-based method is 100 times faster than this method.
Okay,
Maybe.
Thank you. Let's thank the speaker again. Right, the second talk is called Avengers Assemble, Supervised Learning Meets Lattice Reduction, a single power trace attack against Crystal Kyber key generation by Damien Marion, Nguyen Nguyen, Alexandre Wallet, Pierre-Alain Fouque, and the speaker is Alexandre Wallet.
Thank you for the introduction. Hello everyone, good morning. Thank you for attending this talk. My name is Alexandre, I work at PQ Shield, and I'm very happy to be here and tell you about this joint work with my collaborators Damien and Pierre-Alain from Rennes University, and my, at that time, student Nguyen, who now works at IDEMIA. So, as the title does not suggest, this work is about an attack against Kyber's key generation. So, it means the context is post-quantum cryptography. And if you've not been aware of what's happening in post-quantum cryptography, well, that's a shame. But what's important is that there's a new post-quantum key encapsulation standard that has been given a FIPS very recently called MLChem. And from any point of view of this talk, MLChem and Kyber are the same scheme. So you can, every time you want, you can replace Kyber with MLChem if you want. So what we are going to see today, I can sum up in these 4 items there. So our target is an unprotected implementation of the so-called CBD sampler in the K generation of Kyber. So CBD stands for Central Binomial Distribution. Our method is power analysis, and our classifiers are drawing on the Hamming weight of something that's outputted by this CBD sampler. We also use a bunch of linear algebra tools, so sometimes it's just plain Gaussian elimination, and there will be a bit of black box lattice reduction, and also something I personally call LWE hints, but maybe it's a bit of another stretch here in that talk. So maybe if you remember the RAM session of Morgan yesterday, it means that this time I'm the LLL team guy inside the side channel place, I guess. Now if I want to sum up completely the attack in just this little equation there, a classifier plus linear algebra gives you secret key. That's the sum up for if you want to keep one thing in your mind for this talk. And the concrete results is that we have a full key recovery against all security levels with a very high average success rate. So the organization of the talk is going to follow the flow of the attack. We are going to go a bit in the training phase and how we dealt with the classifiers. Then I will move on to the attack, and we will see how to go from the power trace to what I call LWE hints, but it means processing the leakage that we will get into something meaningful for the linear algebra phase. And then in the end, I will tell you about how good the key recovery situation is. I also will want to take a little time to compare with other talks that were presented at this conference. So yesterday there was a nice talk on a similar attack. I want to compare to see the different features of both works. And I also want to differentiate with another work that's going to be presented tomorrow and hopefully not spoil their talk. Not tomorrow, this afternoon, sorry. And hopefully not spoil their talk. Okay, so let's go. The pseudocode on the left is mostly for completeness. The interesting part for today, I guess, is rather on the right. There are some parameters I want to fix once and for all. So k is going to be a small integer, giving me the size of vectors and matrices. All computations will be done modulo some prime number, which is fixed for Kyber. It's this prime here. From my point of view and for this work, the secret key is not just S, it's the entire vector SE that's sampled by the CBD algorithm here. So these are two vectors of size 256K with small coefficients. And for completeness, the public key is a large matrix with large entries, A, and also a noisy linear solution to the system that this matrix defines. So as I said, the secret key is sampled out of this CBD algorithm, and it's parameterized by this value eta, and there's two values that are interesting. Eta 512 is for the lower security of MLChem, so NIST 1 standard, if you know what this means, and the value is 3. And then for the largest, security level, highest security level, the value of eta will be 2. And it gives you the magnitude of the coefficient in the secret key. So if eta is 2, your coefficient can be anywhere between -2 and 2. And for the side channel purposes, the main focus will be that particular step. So this difference is really what we want to target during this attack. So our setting is as follows. We did the acquisition on a chip Whisper. There were 4 chips that we trained and compared against. We had 2 implementations of the CBD algorithm, one by value of eta. And for any combination of chip and implementation, we did 20,000 traces. Now, if you look inside this algorithm, there are 2 loops, and actually what this means is that each execution outputs you actually 256 differences like this here, A minus B, and so it means every execution we have actually 256 subtraces that are interesting for us. So gathering everything, we have 8 data sets, about a bit more than 5 million subtraces. We have done the split training testing in 80-20 proportion, and in total we had, I think, 16 classifiers trained on Hamming weight, as I said. I want to take a brief moment to advertise the cool work of my co-author Damien on this. So he made a whole artifact submission that we presented at the Optimist workshop on Sunday. So it's there on this GitLab. I could not reproduce the QR code, sorry. Computer scientist here. Then what you can find on this GitLab is the whole data sets that we use, all our training, all our testing sets, also all the acquisition code, but actually the whole complete code from acquisition to processing the thing into linear algebra, and also the code for the linear algebra phase, so you can reproduce everything if you want. Okay, now let's go on to the attack, let's say. We did some leakage analysis, assessment, and what we observed, so we compared many distributions. There were the difference itself, the value, the Hamming weights of each of operands and their values, but also this sign of the difference. And what we observed is that there was a very high correlation on this distribution, so the Hamming weight of the difference, and also the positive versus negative situation. And actually, the positive versus negative was so identifiable that we could do complete separation of the situation. So if I want to sum this up, we always knew exactly the sign of anything that was computed by CBD in the end. And that was useful to us for the next steps. So we had trained some classifiers. What we observed is that the accuracy was not really much of a problem. It was rather high. So the problem is that it was not completely perfect, of course, and that was a problem for 2 reasons. If we could not trust the results, it means that maybe we had wrong values that we would process to the linear algebra phase, and then it would mean that we would compute garbage in the end. So we could not tolerate any mistakes in anything we take. And a secondary reason, I'd say, it's an attack against the key generation. So we can only do a single trace. We cannot reobserve some execution or whatever. So we had to do everything with the training sets and testing sets we were given. So our strategy for this was to try to come up with a solution to have the most reliable, let's say, predictions. So on the testing set, once we had trained our classifiers, we had some labels. So it's an input, a predicted class, and the true class, actually. And on all the inputs on the testing sets, we run the classifier, so it gives us a tuple of probability. And then for each classes, among all of this probability for that classes, we took the highest on which this class was wrongly assigned to some label. This gives us a point of reference QC. And then we define the simple function. For the sake of readability here, I called it assigned value, so it makes its role quite clear, I hope. And this function would just give you, on new inputs, it would assign the predicted value only if the probability obtained for that predicted value was higher than the reference point. Else, it would just do nothing, and we would then do the assumption that this is reliable enough, and then we would assume the Hamming weight of the difference here is actually the true Hamming weight. And we will see that actually this assumption was quite reasonable in the end. Then we have the Hamming weight. We don't have the values yet, and so we do have to do a little mapping, but here it was relatively fine. So for eta equals 2, the simplest example here, we separated the situation in positive and negative first, and then we looked at the possible Hamming weights. So if the Hamming weight is 0, there's only one value, it's 0. And if the Hamming weight was 1 on the positive side, then, well, we could not distinguish between these two, so this kind of information we never processed. It was basically, it was considered as not meaningful for us. And on the negative side, here we could always discriminate because of the representation inside the algorithm. So it's a 2-complement representation on 16 bits, and therefore it was easy to see which value it was. And so basically it means we would process all coordinates of the secret that would be 0, -1, or -2 that was distinguished by our classifier before. And so to sum up this whole training phase, as a conclusion, our classifiers in the end will give us a proportion of the secret keys coefficient, which I sometimes may refer as to learning with error hints or LWE hints, or just hints if you want. Before we move on to see how we use this proportion, I want to tell you about the comparison between classifiers to make it a bit clearer what kind of proportion we had. So we compared 3 methods. There was template, decision trees, and decision trees plus ADA boost. In terms of accuracy, everything was rather satisfying with a clear, with a rather higher accuracy for decision tree plus ADA boost. But what's more important for us is the proportion of considered guess coefficients. So on these 3 grids, the situation is as follows. On the vertical, you have the chip we use, say this in English. We use the traces for that chip against for which we trained on. So this is the vertical is the chip that was trained on, and on the horizontal it's the chip we tested against. Then you have a 4x4 grid, and in each square you have smaller square. And what's important for us is the upper square. So each square is the remaining number of guesses. So if this is just 1, we consider we have guessed the coordinate. Else it's 2, 3, 4, depending on the values. And maybe from the end of the room, it's difficult to see the little numbers, but what you can see is the colors. And since the upper left square is the most important, you can see that clearly here, we have a lot of guesses compared to the other situations. So the classifiers are actually done with this decision tree plus ADA boost methods. And you can see, if you cannot read, I will tell you. Here, for example, we have up to 56% of the secret that we have found and considered guessed. And the lowest, I think, is here, 39%, 37 here we have. So this is the kind of proportion of coefficient of the secret key we would have guessed. And now we will move on to the attack phase, let's say. So the power trace goes into a classifier, gives us a proportion of things. And now we're going to see a bit of linear algebra. I will keep the learning with error side to the minimum. From the point of view of this talk, learning with error is just a linear system. You have 256K equation and twice the number of unknowns. So it's an underdetermined system. Now what's the hint? For this talk, there's only one kind of hint called a perfect hint. You learn a linear combination of the secret key. So here, I say this is a bit of a nervous stretch, but because I learned exactly a coordinate. So it's a very simple linear combination, but for the formalization, it's better this way, I believe. And so every time I learn a hint, I add a new equation, basically. So there's 2 takes we can see here. First of all, the real dimension of the problem, even if I have twice 256K unknowns, is 256K. And also, if I have more than 50% of the vector SE, the secret vector, I'm done. It's finished. The problem is completely determined. It's going to be easy to break the rest. And we will see that this is often the situation, actually. Yeah, so we have these coordinates, these hints. I guess I will tell you how we process them into meaningful phase in linear algebra. I will use the nice picture from my students here. It's, I think, relatively straightforward, but I will walk with you through the arrows. So we have a number of hints on the vector S, HS, a number of hints on the vector E, HE. Dimension is 256K. So first thing, we have a lot of equation on which we know the noise component, so we remove that noise and we have now a bunch of linear equation only. And on this linear equation, we know a bunch of unknowns, so we restrict them. So effectively, now I'm here. I have restricted, I have shrunk my linear system, and now the dimension is much lower. And then we do a little more of processing to have a, let's say, systematic form. And now there's two regimes that we have to distinguish that will tell us exactly how we can handle the next phase. It basically depends on the size of the linear system here. It's not always a tall long matrix, it could be a tall one. And the two regimes are as follows. There's one which we have called way too many hints. So you have so much hints that you have more than the dimension of the problem. As we have seen before, the system is overdetermined now. You just do Gaussian elimination, and with the size of these systems, it takes, I put less than a second, but it's actually rather in a microsecond, I guess. And the quick take here is that for the higher level of security, this is almost always the situation we were in. So we got some hints, and then in the end, we just press the button, key comes in a microsecond. So all the work was done with the side channel. And sometimes we were not as lucky, we had a smaller proportion. Now we fall back to the normal cryptanalysis regime. If you know about this, we also call it primal attack sometimes. The secret key is usually short vector in some lattice of dimension much smaller than usual. And so we can run some black box lattice reduction on this. We still have to estimate the parameters, but they are entirely dependent on this proportion here. So really the driving parameter here will be that proportion. And again, if you do not wish to know how we exactly predicted this, the quick take is that if the proportion is higher than, let's say, 35%, you can break the whole, you can finish the key recovery on the laptop on the weekend, which is a trendy cryptanalysis unit, as I mentioned on the slide. So it means the attack is very practical. Now still, I have to tell you a bit about this prediction. So the tool is BKZ. It's a block lattice reduction algorithm. We use a black box implementation in Sage Math, so no fiddling with the implementation at all. Its complexity is an exponential function of the block size. Since it's a block lattice reduction, it operates on block in matrices. And to estimate that block size, there are standard cost models. I won't bore you with all of this. What's important here is that there is basically this prediction gives you a minimal value, and you know that if you increase enough, at some point the key is going to appear magically. So in our experiment and attacks, what we did is starting with this prediction, run BKZ, it outputs something short. If it's the key, we're done. We can check this very easily with the public key. If it's not, then we just increase a bit the block size, and we do this until either we get the key or we reach the arbitrary threshold of 65 that we had given ourselves. What you can see on the picture is that the prediction seems a bit optimistic. So there's an offset here, which I actually cannot really explain. But what matters to me, rather, from the point of view of the attack, is that it's not so far off the prediction. So at least we do not need to, for example, go from a low block size to, I don't know, something horrible there. Okay, so somewhat that concludes the attack phase. Now we are going to see some results. So this is the same presentation as before. So trained chip, tested chips against. We did a bunch of instances, so 1,000 for 512, and for the higher level of security, a bit less, but still of the same order of magnitude somewhat. Same presentation, but different content. So now the small subsquare contain the proportion of recovered or not recovered key depending on the method. So the most important is there a zero in the upper left square? If yes, it means complete success on these all instances. If not, sometime it failed, and we can see quickly that it has failed very few times on this, and then there is this very annoying, for let's say statistic purposes, outlier here. For some reason on this combination we have just above 50% success rate. also not be able to tell you why, but let's say that overall, the success rates are very satisfying in the end. So I will take a little time to compare with the nice talk of yesterday's afternoon for the first iteration of this session. So it was a similar attack, targeting also the CBD in Kyber. The difference is we only targeted the keygen, and they were targeting all possible execution of the CBD sampler during any of the triplets of algorithm. Their classifier, if I remember properly, was they tried to do it on the Hamming weight of A and B and could not manage to find something really meaningful. But they found another indicator that was nice, which they called buff. If you are interested in the detail, you can go to check the replay or their paper. And we have seen that our classifier was on the Hamming weight of the difference or this positive negative thing. In terms of accuracy, that was not the main focus for us since we had lattice reduction in the end. For them, it was very important that the accuracy was very high, so they managed to do this, if I remember properly again. And then, so actually these two lines are somewhat dual of each other, let's say. We didn't need a very high proportion of coordinates to be guessed because we had lattice reduction. But that means also that our success metric was a bit different. For us, success was we get the key in the end, whatever that means. For them, the success metric was at the end of the side channel phase, we have to get the key. And so, to be fair, here is just saying the comparison is just to see that they were not having the same success metric. But of course, that both work could be combined there. Of course, they could probably relax a bit their condition of success and use lattice reduction to finish. I guess the most important item there is also that our attack works against any security level, and theirs was restricted to Kyber 768, so the second security level. And so again, I think the natural approach is to do just both works in the same go, and then you have an attack that's going to be efficient enough. I said I also wanted to differentiate with the talk of this afternoon and hopefully advertise a bit for them. In the title, there's also hints, there's also lattice reduction, there's also Kyber, there's also KEM, there's a lot of words that are the same, but in the end, it's very different. So the quick take is it's two different attack styles, targeting very different leakage, providing very distinct hints, and we do not exploit them in the same kind of lattices even. So it's actually, when you look in details, it's not at all the same work. The common point is there's lattice reduction in the end to complete the attack. To talk about the different hints, for the sake of completeness, so we had perfect hints, very simple perfect hints, and because of the type of leakage they assess from the Hertz bleed, I'm actually not sure what Hertz bleed is, so I just say the name here. It provides modular hints, which means linear combination, but you know them only modulo another integer. So these are a bit less interesting from a pure cryptanalysis point of view, but they still manage to use them with different lattices than the one I showed you before. Lattices that are related to the number theoretic transform in Kyber, which is the actual thing they attack. So it's also not an attack against the CBD algorithm. So yeah, hopefully we will go and all see what this work is about this afternoon. And I think, yeah, this is the last slide. I'm not going to read you through the whole table. I think they are explicit enough. I think I want to highlight that the our worst success was 37% of proportion of secret coefficient recovered. And we had to go to this beta equals 65, and it took us about a day to finish the computation. So that's still very practical, and that was our highest computational efforts, I think. And I guess the recommendation, trying to anticipate for, I guess, the usual question, is that you should put masking and shuffling in any key generation algorithm inside Kyber, whatever is your deployment context, I guess. Yeah, so that's it for me, and I'm happy to answer any question if there's one.
Thanks for the talk. We have time for 1 or 2 questions, if there's any. Well, I have a few. Well, I'm surprised, and you recommend using masking, and the other talk did as well. And I'm not sure I see the point of using masking to protect the keygen, as it's only SPA leakages. So why not only hiding countermeasure like shuffling, noise, and so on?
Not being the expert, I would say the more the better, but I guess for an efficiency point of view, you could want to have the less possible. I'd say shuffling is already pretty good. I'd say anything that makes the training phase harder is also fine. This is why we would suggest both. But
I mean, it would help, but I was thinking maybe it's an overkill. But, and as another quick question, so you do exploit a lot the fact that you do negative and positive leakages, right? I guess a simple countermeasure would be as well just to use unsigned implementation, right?
that's a good point. I think, yeah, changing the representation would also fiddle with that particular attack, yes.
All right. If there is no more question, let's thank the speaker again. And the last talk of this session is entitled Scoop, an optimization algorithm for profiling attacks against higher order masking by Nathan Rousselot, Karine Heidemann, Loïc Mazur, and Vincent Maiguerou. And the speaker is Nathan Rousselot.
So, hello everyone. So my name is Nathan, and this is a joint work with my PhD supervisors. So the work is called Scoop, an optimizer for profiling attacks against higher order masking. So I will not go into the details of side channel attacks because you're all very knowledgeable about this topic. All I want to clarify is that we are in a profiling attack scenario and that we are interested in deep learning-based side channel attack. So basically, we want to train deep neural networks to perform side channel attacks. So when you train a deep neural network, what you do is you minimize a loss function. And usually for deep learning-based side channel attacks, what you do is you minimize either the cross-entropy loss or the negative log likelihood loss. They are both equivalent. So what you can do when you're training the model is visualize those losses, as shown in this slide. And you see that the losses converges nicely. So they go from a randomness regime, and once they cross the randomness threshold, then they will gain information and converge hopefully to an optimal model that is below the randomness threshold. So this is a standard training of a model against simulated, not protected secret inside channel measurements. So what you can do to protect against deep learning-based side channel attacks? Well, you have several countermeasures actually, and the one that is the most studied and that we will see today are the masking countermeasures. So masking countermeasures consist in uniform secret sharing according to a certain recombination law, such that you have for order n plus 1 random shares that are statistically independent. And if you have access to a strict subset of those shares, then you gain absolutely no information about the secret. So an example of a masking scheme is called the Boolean masking, and it is the most popular one. And it is basically just a masking as per the definition, but with a XOR recombination law. Masking schemes are very handy because they provide a theoretical guarantee in terms of security. So as you increase the order of the mask, then you will exponentially increase the security of your system. However, it is a very costly countermeasure, so you cannot afford, for example, in embedded systems to have a very high order masking scheme. So what happens now if you train a deep neural network against a masked implementation? Here you have an example of a first order Boolean masked AES, and we train a small model on it, and you see that the training loss curves are very different actually to the one we've seen before. So instead of having an initial convergence, what we see is that for several epochs, the model completely stagnates, it stalls at, in this case, at the randomness threshold. So that means that here, for example, during 150 epochs, the model will have learned absolutely nothing, or at least will act at best as a random predictor. So this is very annoying, and it is a phenomenon that has been observed in the presence of masking. And it also happens, I want to precise that, in this presentation, we are a non-worst case scenario. That means that even in the profiling phase, we don't have access to the shares. So this phenomenon is called the plateau effect, and it is actually quite concerning phenomenon, because even if it annoys a lot the attacker, it's actually completely independent to the level of the security of your device. So having a long plateau does not mean that once you get out of it, you will gain little information. you might gain a lot of information, even maybe like old information, but you need to struggle through this initial plateau. So of course, like for example, a certification lab, if you have a limited time budget, maybe you will not be able to get out of the plateau in time, and so you will give a positive result of the evaluation. However, if you just had a bit more time, then maybe you would have seen a huge leakage. So this is a big problem with the plateau. Just to give some an idea of the time it can take, on very expensive and costly architecture such as transformers, one epoch can easily cost few hours to compute. So you can see, for example, 150 epochs that takes a lot of days, and you have no idea if the model is wrong or if you are in the plateau. And the worst thing is that you have this plateau, but this plateau also gets exponentially longer as the masking order increases. So here you have a figure that I stole from the paper Don't Learn What You Already Know. And you can see that on simulated traces, the plateau length actually increases exponentially. So for example, at order 4, you have a plateau length of several thousands of epochs. And in the paper, the author suggested that this might be due to the choice of the optimization algorithm. And this is quite interesting because in the community, optimization algorithms have been a bit empirically studied, but there are no real theoretical study of the optimization challenges in deep learning side channel analysis. What is usually done is that we have a grid search and we just put Adam and its variants, maybe RMSprop as well, and we hope that the hyperparameter optimization finds the right algorithms. So there are no clue that we can do to make well-informed choices to make a good choice of optimization algorithm. So this is really the purpose of this talk. It is first to try to understand the different optimization challenges of deep learning side channel attacks, and maybe then design an algorithm that is well efficient against those challenges. So first, let's recall how we train a deep neural network. So usually what we do is we train it with the gradient descent or any of its variants. Adam is a variant of the gradient descent. And so you have the usual update rule that is given here that you're maybe familiar with. This update rule actually can be rewritten in a different way, this way. And you can verify that this update rule that is formulated as a sub-optimization problem has a solution that is given by the usual way of writing the gradient descent. So why do we want to write it this way? Well, you will discover later in this talk. But just to explain a bit what we are seeing here, we are seeing two terms. The first term is the loss term surrogate, and the second term is the proximal term. And for those who are used to it, the proximal term actually looks like a regularization term. So why gradient descent might struggle, and how come we can have a plateau with such an algorithm? Well, we rely our analysis on a theorem which is not dedicated to deep learning, side channel attacks, but just to deep learning. And we formally call it the CHES theorem, which when translated to side channel attacks basically means that if you have masking order n, and you consider any deep neural network with parameter theta, then the variance with respect to the data of the gradient of the loss will decrease exponentially as we increase the masking order. So what does that mean? That means that the gradient, which literally tells you where to go in the optimization process, has a variance that vanishes as you with respect to the data you input to the model as you increase the masking order. So if you have a very high masking order, that really means that whatever the data you put in it, then the gradient will make a random direction and maybe a random step size as well. And so it will be a random predictor. And this is a problem for gradient descent, of course, because when you look at the loss term surrogate, well, it depends on the computation of this gradient. And so that is why the gradient descent actually fails and exhibits a plateau. So in the paper, we did some simplification of the deep learning side channel attack paradigm to make a theoretical analysis of it. I will not detail the developments, but here are two interesting results that came out of this study. The first one on the left show that the magnitude of the gradient decreases exponentially as we increase the order of masking. So what that means is that the size the step sizes induced by the gradients will decrease exponentially as we increase the masking order. And the second one is related to the Schwarz theorem. It is the variance with respect to the data of the gradient. And we see that it also decreases exponentially and follows actually the same slope as the Schwarz theorem. So these exponential decays are very annoying, and currently there is no found solution to fight them. What we propose is a slight boost of the gradient descent by using second-order algorithms. So what are second-order algorithms? Well, first, let's look back at the gradient descent. We say it is a first-order method because it is based upon the computation of the gradient, which is the vector of the first partial derivatives. So now if you look, for example, at the quasi-Newton descent, it relies on the computation of the Hessian matrix, which is a matrix composed of second partial derivatives. Hence, we say it is a second-order method. The second-order methods are very handy because it is basically a learning rate scheduler that is adapted to the local curvature of the loss. So it will not only look at the ascending direction, but really the entire curvature around the weight it's at, and it will take the best possible choice in function of this. And actually, in a convex setting, the second-order method, and more specifically the exact Newton method, is the optimal descent. So why are they not used? It seems that they are just theoretically better. Well, I guess you know it. It's very computationally difficult to compute the Hessian. To illustrate this, let's consider a model with 1 million parameters. If you just do gradient descent, it's very easy. You just have to compute a vector. With backpropagation, it's linear, and everything is linear, really, in the number of parameters. But when you want to do second-order method, you also have to compute the Hessian, and the computation and storage is n square, and to use it, you even have to invert it, which is even more expensive. So obviously, this is not tractable and not usable in practice. However, all hope is not lost because there exists a family of second-order methods that are called inexact Newton method, which basically is you do not compute the exact Hessian, but just an approximating operator. And the most common choice is the diagonal. So if you manage to compute just the diagonal of the Hessian, well, you will still include second-order information, but we know methods to compute the diagonal of the Hessian that are linear, and then you have a vector. So everything is linear, and you can do second-order method linearly. The second observation emerges from the usual assumption that we make on the leakage points. We say usually that points of interest in side channel traces are rare and sparse in the measurements. So from this observation, what we do is that we will make the hypothesis that the optimal model is sparse. So that means that most of the weights of the model are either small or close to zero. So what it means that we want the optimal model to have a certain structure, and to impose a structure in a model, what is done is we do regularization. And if you remember, when I introduced you the second notation of the stochastic gradient descent, I showed you the proximal term, and this proximal term, I told you, it looks like a regularization term. So what we will do is we will remove the proximal term. So this proximal term is actually an Euclidean distance. So what we propose is to remove this by a generalized distance that's called the Bregman divergence, and we obtain a new algorithm that is known as the stochastic mirror descent. So the Bregman divergence is a divergence that is driven by a certain potential function psi, and it is the first Taylor expansion of psi. So what is good with this algorithm? It is implicitly psi regularizing. So if you train your model with the stochastic mirror descent, then you will impose a structure to the model with respect to psi. So if you choose psi to be the L1 norm, well, the model will converge to a sparse one. So mirror descent is a bit of an abstract topic. So what I propose is to simplify it a bit in this slide. It's really only 3 steps. So first, the mirror descent projects the weights of the model into a dual space. So it will come from an Euclidean space, which is the standard space in deep learning model, and it will project them on a dual space that is spanned by psi. In this dual space, it will perform a gradient descent step, And once the gradient descent step is done, it will project back the weight onto the primal space. So we now have two ingredients. We have the second order method and the stochastic mirror descent. And our proposition to address the different changes of the optimization process is to combine the two ideas. And this really is what Scoop is. So you have the update rule that is given here. So Scoop is a second order method that is based on the estimation of the diagonal of the Hessian. And it works in a dual space. So it is a stochastic mirror descent. And for the choice of the potential function, we choose the L1 plus epsilon norm. We cannot choose the L1 norm because, as you saw, the Bregman divergence is a first order Taylor expansion. So we need the potential function to be differentiable. And L1 plus epsilon allows us to be sparser than gradient descent while remaining differentiable. So we have several results with Scoop. The first one is on simulated measurements. So we consider simulated data that implements a Boolean masking of order n. And the most important thing is that those data sets will be exhaustive. So that means that we will feed the model all the possible combination of shares. This way we remove completely the challenge of generalization and we really simplify the problem from a learning problem to an optimization problem. And we have a fair comparison point between all the optimizers. So we will compare Adam and Scoop on a free architecture, MLP, CNN, and transformer. So here are the results. You see that whenever there is masking order equal 1 or higher, Scoop effectively reduces the plateau size comparing to Adam. And actually, we see that, for example, for the MLP, we gain approximately 1 order of masking for the attack complexity. However, we see that the trend is generally the same. So the complexity with respect to the masking order is the same. We've basically gained just a constant. So we will see a bit later why. On real data sets, we tested first on ASCAD V1. So ASCAD V1 is a very used data set. We've seen it many times in this week. It implements first order Boolean masking. And when you train an MLP, for example, on it, we obtained these training curves. So we see that there is a plateau of 35 epochs. And what we do to compare it with Scoop is we remove Adam and we put Scoop instead, but we keep all the same hyperparameters outside of it. So we just change the optimizer. And by doing so, you see that we went from a plateau of 35 epoch to virtually no plateau at all. So we had a great reduction of the plateau and a much more efficient optimization process. So one can wonder, is Scoop just only benefiting from the Hessian? Is Scoop only benefiting from the stochastic mirror descent? Or is it using both? Well, we tested this on ASCAD V1 as well, with VGG-like CNN. So for the baseline, we will take Adam. The idea is not to make state-of-the-art attack, it's really just to put comparison points between the optimizers. So we see with Adam that we nullify the guessing entropy with 180 traces, and we have a plateau size of 23 epochs. If we use Sophia, which is an inexact Newton method, so second order method, we see that we have an improvement in both guessing entropy and plateau size. If we perform the optimization process with the standard stochastic mirror descent, we also have a nice improvement. And when you use Scoop, well, we still have a plateau, so that doesn't change a lot between Sophia and SMD, but we still gain some performance on guessing entropy compared to the two other methods. So we still see that there is an edge by using the two. So Scoop really uses both mechanisms that are not doing the same things. Now for a last result, we targeted ASCAD V2. So ASCAD V2 is much more challenging than ASCAD V1. It is still an AES, but this time with affine masking and also shuffling. So we've trained an MLP with all the 4 optimizers I've shown you just before, and all failed, but one with Scoop, where we obtained some information. So as you can see, the loss crossed the randomness threshold, and the guessing entropy seems to converge nicely. So this is a very cool result because in non-worst case setting, it remained an open problem. However, after we published the paper, like few weeks after, ANSI reached out to us, and so we published the artifact, and they kind of studied our model and all our code, and they discovered that on the ASCII-V2 dataset, and specifically on the byte we targeted, there is a bias, so on byte 4, and they actually discovered that the byte 4 of ASCII-V2 was not following a uniform distribution. Hence, by doing so, when we train your model on a biased input that leaks very little, then the model, instead of learning the distribution of the secret, knowing the traces, it will just learn the marginal distribution of the secret. And so the attack is hence not valid. It did not break the implementation per se. And actually, it's not only a fourth byte. There is also byte 2 that is affected. And we've done also further analysis that tends to think that other bytes are also flawed. So to conclude this talk, so we have designed an optimization algorithm that is called SCOOP that combines a stochastic mirror descent and a second order method. And on the real and simulated cases, we observe some gain. On simulated cases, we see an empirical gain of 1 order of masking in attack complexity. And we see great reduction of the plateau in real cases as well. So I was talking to you that there is still the same complexity when we looked at the plateau with respect to the masking order. And this is actually due to the fact that, well, we still rely on the computation of the gradient. So if you recall the CHES theorem, where the gradient completely loses information as the masking order grows, where here we have the same problem. So a solution to this would be, for example, to find an alternative to any gradient-based optimization, but they are known to be intractable for deep learning side channel attacks. So if you want to play around with Scoop, there is an artifact available. It's very easy to use, so it's implemented in PyTorch. All you have to do is remove your optimizer and put a line Scoop. And you also have just to put one line in the training loop additionally to make the Hessian update. But all the documentation is given. So feel free to play with it. And if you experience some curious things or you just want to ask questions, feel free to reach out as well. Thank you very much for your attention.
Thank you. We have time for a few questions. I'll start again with one. It's more of a remark. On the conclusion you were mentioning about the exponential complexity of the profiling phase, I was wondering, from a theoretical information perspective, when you don't know the shares, I mean, when you don't know the randomness, you have to estimate higher statistical moment. So, I mean, I don't think it can be done, right, to break the exponential property.
Well, the curious thing is when you look at these figures, these ones. So it's simulated traces, but there is, I didn't say it, lack of time, but there is no horizontal noise. So the challenge of recombination, it doesn't need to find the samples in the trace where to recombine. So we cannot break this usually exponential complexity because the points are just there.
I don't think it comes from the horizontal noise. It's just the property of exploiting higher the statistical moment is just exponential. I don't think you can break it anyway. Okay. You're exponential, but you get a fixed benefit. Right?
Okay.
I'm not sure, but we can talk about it. Is there any other question? Okay, then let's thank the speaker again.